All right, so questions? Absolutely.
So, I tried to do the delete function.
Mm-hmm.
It's deleting,
Mm-hmm.
but the issue is when I do the dump command, it still shows the plate, but the plate's not there. Like it says.
Okay, so the node is like still there, but the data's been deleted or something.
Yeah.
Interesting.
So, I mean, I guess we should have class, but it's definitely, it's doing what it should in a way.
So the most likely cause of that is something related to not returning the root correctly.
No,
Okay, so if you delete the root, you want to return null. Okay, anything else you want to set root left or root right equal to the recursive call to delete, and then just return the original root. Okay, if you're doing those things, the plate should disappear.
The question is where's the problem?
Yeah, but double check the code and make sure if you delete the root node, you do, whatever it is we're doing when we do stuff, right? The first day we talked about delete and return the new root of that tree, right, which will be the largest thing in the left subtree. Otherwise, set root left equal to delete or set root right equal to delete and then return just root. Okay. And try it with a small tree. Make a database where you have just 3 nodes and try deleting the root and see if that works. And then try just deleting the left node and see if that works. Yeah, try to pin it down like that. And then once you have a test case, that's not bad to go through GEB if you have to. But you might find it just by looking at the code after a bit of a break from staring at code.
True. This was the last thing I did.
Yeah, okay. Yeah.
So, when I run my code through Valverde,
Mhm.
it gives me a bunch of errors, like when I use string copy in my
Okay,
program. Like it says everything's free, like there's no limits,
Good,
but
good.
It brings up a bunch of errors and it's like,
okay, are you malloking space before you string copy?
yes.
Okay, are you malloking space based on string length plus 1? You're definitely adding 1. Okay. Usually that's the result of not mallocing the right amount of stuff. So when you malloc the node, are you mallocing based on size of struct node as opposed to struct node star? Okay. So basically malloc for the node based on size of struct node, and then malloc for plate first and last based on string length of plate first and last plus 1. Don't use size of. Okay, make sure it's string length. Because size of a string is always 8. And
Oh, so I did size of, yeah,
Size of plate?
String length of plate plus.
okay, yeah, just do string length of plate plus 1. That's the number of bytes you need. Size of that will just be 4. It's the size of an integer. Size of is a bit of an unfortunate command because it gets us into lots of trouble. And we really don't need it except when we have no other way to tell how big something is. Right? If you can do string length, do string length. If you know how many bytes you need, use that number of bytes. But if it's like, how many bytes do I need for a struct node, we don't know that. Right? We have to be the architects who wrote the compiler to understand that. So string length comes to the rescue there. But other than that particular situation, we can just stay away from size of. I think I said string length instead of size of there, but you know what I mean. All right, other questions? All right, so a few announcements. Number 1, I posted an announcement. Scott is teaching a machine learning class in spring. It's a CSE 280, Monday afternoons 3 to 5. So 2-credit course. If you have room in your schedule, you might want to check it out if you want kind of an overview of machine learning and that kind of stuff. Should be a cool course.
Is it going to be in C?
Python and something else, but he's planning to go over the Python that you need, and he's planning to go over the linear algebra that you need.
Oh, okay.
So it should be totally accessible for everybody here.
Sweet.
Yeah.
Do you know what other, like requirements are there for the class?
Yeah, I think Calc 2,
Okay.
which I'm thinking everybody in here is fine with.
Do we need physics?
I don't think so.
Good. I may be in it, but don't know if I would match the prerequisites.
Yeah. Well, there's taking a course, there's passing a course well enough to move on, and there's understanding the course. And
Then it's mutually exclusive.
yeah, I mean, I have a bunch of degrees. I have a PhD in electrical engineering. I did not learn KVL, KCL till I came to Clark, and I started teaching 120.
Whoa.
And the first quarter I taught it, I was like, oh my God, what is this stuff? And I had some recollection of late nights with Chinese food and trying to figure this stuff out. And I had to learn it, right? And it took me about a year, of teaching it before I could actually say I finally understand this, right? But it didn't stop me from, being able to use it and take other courses and pass and graduate and so on and so forth. So there's degrees of familiarity with things, right? And physics is very much that way for me. When we do assessment work in the spring, a lot of times we get together with Gothard and we use some of his exams to do the assessment analysis, which means we have to know how to solve the problems on some of his exams. And so he starts the morning by giving us a little physics lecture, and we somewhat understand how to do some of these things. Even though we all took physics and we all passed it, eventually and stuff like that. So yeah, there's degrees of understanding. The stuff you need to use, you'll work with enough and you'll understand it as well as you need to. So. All right, so other announcement. I've posted the final exam study guide on Canvas already. And some of the things on there we've gone through, some of them are down the road for us. But I want that posted up there because I want you to understand that everything we're talking about is fair game for the final, okay? And the final will probably be a combination of some programming questions and some non-programming questions. So today and tomorrow, for example, we're going to work with balancing binary search trees. And we'll talk about it. I'll give you the algorithm. I'll show you some examples, and then you'll break into groups and work on this on the board today and probably part of tomorrow. And you might see a question on the final about that, okay? So, so keep coming to class, okay? Because a lot of this stuff, balancing trees, queues, things like that, are not going to show up in programming assignments, okay? But there's still things that you might see on the exam. We talked about queues yesterday. You might see something about queues. Either conceptual question answer, or here's a queue, show me how these operations modify it, or things like that.
I guess this is how we tell people watch lecture videos.
Yeah. All right, so let's talk about tree balancing. And remember, the basic idea here is that when you have a binary search tree and you want to do things like find a piece of data in it, not all trees are the same, right? This is a tree that has 7 pieces of data in it, and this is another tree that has 7 pieces of data in it, okay? This one is going to take a lot longer if we're searching for something that happens to be the largest value in the tree. This tree, same amount of data, to get to this largest value is going to take us 1, 2, 3 operations. So in general, for a nice full binary search tree containing n pieces of data, it takes us roughly log n operations to search, insert, delete. Okay, that's only if it's a nice full tree. If we have n pieces of data and our tree is just a big sideways linked list, it's going to take us n operations to search that list. So to get this log n efficiency, which is the whole reason that we're dealing with trees instead of lists, we need our trees to be balanced. Okay, and we had a definition of balanced, right, which was the left and right subtrees differ by height no more than 1, and the left and right subtrees are balanced. So the challenge is you're building a binary tree you get in a 10, you get in a 20, you get in a 30, and if your data happens to be coming in the wrong order, you don't get a balanced tree, right? And now I might get a 5, and a 4, and a 3, and a 2, and a 1, and this is really not a well-balanced tree. And you know, everything I get is going to get added to a leaf node, so these might get filled in at some point, but in general, you just throw stuff into a tree in whatever order, it's not going to stay balanced very long. And there's not a good algorithm for taking a tree like this and balancing it. Okay, there's a lot of complexity there. What is doable, though, is if you have a tree which is currently balanced and you add one node to it, and now it's unbalanced, what can we do to make it balanced again? Or you have a tree that's balanced and you delete one node and now it's unbalanced, what can we do to make it balanced again? Okay, and that's not a bad algorithm. That's what we're going to talk about today. So the setup is you've got a tree that's already balanced, you're adding or removing a single node, and now it's unbalanced. How can we correct it to restore balance? And we can't, you know, just take the 50 and put it here, and take the 40 and put it here, and put the 1 over here, and the 2 over here, and put the 3 over here. Yeah, that's a nice balanced tree. It's not a binary search tree anymore, right? BSTs always have this property that at any point in the tree, everything on the left is smaller, everything on the right is larger. So we want to restore balance in a way that does not disturb it from being a binary search tree. Because if it doesn't have that BST property, we can't do our efficient recursive searches, inserts, deletes, and so on. So let's insert some data into a tree. Let's insert a 10, that's going to be our root. Let's insert a 20. And this is still a balanced tree, right? Balanced, left subtree is balanced, right subtree is balanced, and the difference in height, this has a height of -1, this has a height of 0, so the heights are within 1 of each other. So this is still balanced. But when we insert the 30, that's not going to be balanced anymore. The reason being, if we look at the root, the left subtree has a height of -1, the right subtree has a height of +1, those differ by 2. So at this point, we've got a balance problem. All right, so first thing we need to define is something called the balance factor. So the balance factor of a node is the following. It's the height of the left subtree of that node minus the height of the right subtree. Balance factor is completely different from height. It uses height to calculate it, but it's not the same as the height of a tree or the depth of a node. Okay? It's this formula, take the height of a left subtree, subtract the height of the right subtree. And every node has a balance factor associated with it. All right, I'm going to put balance factors in parentheses. So if we just look at this node 30, what's the left subtree? And what's the right subtree? Okay, and those both have height of -1. So -1 minus -1, that's a 0. So this has a balance factor of 0. Okay, what about the 20 node? What's the left subtree? Right, null, which has a height of -1. What's the right subtree? It's just a 30. What's the height of this tree?
1.
Almost. No. Colder. Warmer. 0. Right? So a tree with just a root has a height of 0.
Sorry, I thought you were celebrating the 21st moment.
Oh, okay. All right. So left subtree is null. That has a height of -1. Right subtree is just a 30. That's a height of 0. -1 minus 0. That's a balance factor of -1. You with me? All right. Let's find the balance factor at the 10. So the left subtree is null. That's a height of -1. What's the height of the right subtree? Almost. Don't look at the balance factor, it's just the height of the tree. So the height is 1, right? So the number of steps from the root to the deepest node. So minus 1 minus 1, this has a balance factor of minus 2. All right, so here's the thing. A tree is balanced if and only if the absolute value of the balance factor of a node is less than or equal to 1 for all nodes. So if you find the balance factor at every node and it's less than or equal to 1, or bigger than or equal to -1, the tree is balanced. Once you find a factor that's bigger than 2 or less than or equal to -2, the tree is unbalanced. Okay, so that tells us this tree is not balanced. But because it was balanced before we added that last node, there's a simple manipulation we can make to rebalance this tree. Okay, and this is going to be something called a rotation. So the essence of this, and I'll show you the details in a moment, but the essence of this is this particular tree is unbalanced because there's too much stuff on the right. Okay, we have a node here, a node there, and a node hanging down at the bottom. And it's what we call a right-right imbalance. Okay, we've got a node up here at the top, we've got something hanging to the right, and another thing hanging to the right. We can make that balance by doing the following operation. Take these 3 nodes and reshape them like this. Bring that first node, that's the root right now, down to the left of this middle node and leave this other node on the right. So this is called a rotation. And the sense here is we're rotating around this 20. And what it's actually going to leave us with is the following tree. And this is nicely balanced. Every one of these nodes has a balance factor of 0. And so this is from Wikipedia. These are called AVL trees. Okay, and there's 4 possibilities. If our tree was balanced and we just added a node and now it's unbalanced, there's 4 possibilities. Somewhere there's a node with a balance factor of 2 or -2. Okay, if we look at its children, if we have a node with a balance factor of 2 and its left child has a balance factor of 1 or 0, then we're in this case where we can basically just rotate that 5 down to the right and turn this into that. If we have a node with a balance factor of -2 and its right child has a factor of -1 or 0, that's the case we just had, right, -2 and -1, then we can basically take this 3 and bring it down to the left of 4. Okay, so let's look at what we just did with the right case. We were rotating around the 4. We're going to bring the 3 down to the left of 4. Well, 4 already has a left child. Okay, but once we bring 3 down, 3 has nothing on the right, so 3 is going to adopt what 4's left child was on its right. And 5 doesn't enter into any of this at all. It's just going to stay there. It's going to have children C and D. And the left case is the same. We're going to take the 4 and the 5. We're going to rotate the 5 down. So 5 will be the right child of 4. 5's left child is free to adopt 4's former right child C. But if I didn't want to think too hard about this, here's what I would do. I would label my picture. And I would say, okay, my node with a factor of -2, that's node 3, so I'll put these in boxes. The left child is A, that's null. The right child is node 4. 4's left child is B, that's null. 4's right child is node 5. And its left and right children, C and D, are null. And then I would transform it into this balanced case, which says the new root should be node 4, which is 20. 4's left child should be node 3, that's the 10. And 4's right child should be node 5, that's the 30. So that's how I get from there to there by following this. For simple cases like this, we can just sort of do this in our brains, just take this and flip it down. For more complex cases, that's error prone, and that doesn't work when you're writing code. You can't write C code that says, well, take this thing and bend it down to the left and push that up. But this will map directly into C code. I'll show you some code tomorrow to do this. All right, making some sense? Okay, so remember, balance factor is the height of the left subtree minus the height of the right subtree. Okay, when you're computing balance factor, don't look at the existing balance factors. It has nothing to do with balance factor. Balance factor is just based on heights of subtrees. So we've got our tree 10, 20, 30. Let's insert a 40 into it. So 40 is going to go to the right of 30. And let's put in our balance factor. So this will be a 0, this will be a 0, this will be minus 1, minus 0. And what's the balance factor of the 20? All right, that's also going to be negative 1. Because the left subtree has a height of 0, the right subtree has a height of 1. 0 minus 1, negative 1. Okay, so is this a balanced tree? Yes, because every node has a balance factor with absolute value less than or equal to 1. So that's still balanced. And even if it doesn't look like it, there's really nothing we could do to make it more intuitively balanced. That 40 has to go as a child of either the 10 or the 30. Okay, so let's add a 50. And I'm going to recalculate balance factors. So this will be a 0, this will be a minus 1, this will be a minus 2. I can stop right there. This is unbalanced. And this is again what we call the right case. There's a minus 2, there's a minus 1. And I can label everything very carefully, but the action is that 30 is just going to come down and be the left child of 40, and the 40 is going to move up in its place. So this will be rebalanced using a right rotation to look like this. And that'll be balanced. Okay, let's add a 45. So we'll go to the right of 20, right of 40, left of 50. This will be a 45. Let's calculate balance factors. That's a 0, that's a 1, that's a 0, that's a minus 1, that's a 0. This is a 0 minus 2. This will be a minus 2. Yeah. So there's other ways you can balance this. Okay. The trick is, can you tell a computer how to do it? Okay. We could move the 30 to be a root and balance this better. Okay. But it's hard to describe in an algorithm. All right, are these balance factors right? Because don't trust me. I think they're right. All right, so this is imbalanced. And it's another right case, -2 and -1. So if the right child has a factor of -1 or 0, it's a right case. So let's do this one sort of carefully. So let me put our annotations from here in boxes. So this is our subtree A. This is our node 4. This is our subtree B. This is our node 5. And C and D are the children. They're not going to change. So the right rotation, well, node 4 is going to become the new root. So that's going to be 40. Node 3 is going to go to the left of node 4, so the 20 is going to come down here on the left. Node 3's left child will stay the same, that'll be A, so this will still be a 10. But node 3's right child will be whatever B was. So 20's right child will be B, that's going to pick up the 30, which was to the left of 40. And then node 4, that's the 40, its right child is still going to be whatever it was, that's the 50 and the 45. And that's a nicely balanced tree. Okay, let's put in one more number. Let's insert a 46. So balance factor calculation, this is a 0. This is a -1 minus 0. This is a -1. The left subtree of 50 has a height of 1. The right subtree of 50 is null, that's a height of -1. 1 minus -1 is 2. So we have an unbalanced tree again. And this time, the unbalance is what's called the left-right case. Node has a balance factor of 2, and its left child has a balance factor of -1. Okay, we need two operations to correct a left-right imbalance. The first operation simply changes it to a left-left imbalance. And then we do the one correction from a left-left to balanced. Everybody got the idea where we're going with this? All right, so this is a left-right imbalance. Let's do a left-right correction. So let's label these using this terminology. So this is node 5. Has no right child, so D is null. This is node 3. Left child is A, that's null. Right child is node 4. And 4 has no children, B and C, they're both null. So everything else in the tree is going to stay exactly the same. We're only working with this 50 node on down. And to change to the left-left case, well, 50 will stay the root. So that's still node 5. But its left child is going to become node 4 instead of node 3. So node 4 is a 46, that's going to come to the left. And then the left child of node 4 will be node 3, which was our 45. And there were no subtrees under any of those. So, and the rest of this tree stays the same. So 40, 20, 10, 30. And what we've done is if we calculate balance factors, this will be a 0, this will be a 1, and a 2. We change it to a left-left imbalance. 2, 1, 0. And the way we correct that is we rotate about that middle node, basically bring the 50 down to the right, bring the 46 up to be the new root. So this left-left case, this will all stay the same. But the 46 will move up in place of the 50. The 50 will go to the right. The 45 goes to the left. And that's a beautifully balanced tree.
So is it important when you're doing these multi-step processes that it never stops being a binary search tree? Like it's always ordered relation?
You could have an algorithm where, you know, from here to here it was no longer a BST and then it came back to a BST, but these happen to preserve it in all cases.
Right.
But let's talk about that for a moment.
What is reveal?
3 people's initials,
Oh,
and I do not know what they are,
okay.
but Wikipedia does for sure. So let's suppose we traverse this original tree using left node right. Okay, we're starting at the root. We have to traverse the left subtree, which is this. To make that traversal, we have to traverse the left subtree, which is just A. So our left node right is going to do whatever the in-order traversal of A is. Okay, followed by the root of this subtree, which is 3, followed by the traversal of this subtree. And to traverse this tree, first we're going to traverse B, and then 4, and then C. So everything we get from B, followed by node 4, followed by everything from C. That is the traversal of this. That's the left subtree of the original tree. So then we print out the root node 5, and then we traverse the right subtree D. So this is the order we get if we do an n-order traversal, a left node right traversal of the original case. So what happens after we do our rotation? Well, this tree, we're going to traverse this left node right, which means traverse this left node right, which means traverse the left subtree A, print out the root node 3, and then traverse the right subtree B. That's the LNR of this. Okay, now we're traversing this tree. We did the left subtree, print out the root node 4, and then traverse the right subtree C. That's the LNR traversal of this. So for the original tree we were traversing, we did the left subtree and got this. Now we print the root node 5, and then we traverse the right subtree D, and we got exactly the same traversal order. So we have not disturbed the order of the nodes. And then when we move from there to the balanced case, this one's pretty easy to traverse. We're basically going to do A, 3, B. That's the left subtree, and then the root node, and then the right subtree is C, 5, D, and that's still the same traversal order. So these things are faithful to preserving the property of being a binary search tree. All right, so practice time. So break into some groups, find a spot on the board. One person per group, grab one of these yellow cheat sheets, and we will build some trees, find balance factors, and perform rotations. And you can start off by just inserting a 10 and a 20 and a 30 in that order. Actually, no, I'll give you new nodes. Let's do the same one as the last section. So start off by putting in a 20 and a 10 and a 5. I changed down here. So insert those 3 nodes starting with an empty tree in that order. And then figure out the balance factor for each node. So reminder, the balance factor of a node is the height of the left subtree minus the height of the right. So once you have that, figure out what type of imbalance it is.
So this is,
So that looks perfect in the end, but it's balance factor. So what's the balance factor on the 10? Then you get negative 1.
We're still gonna talk, right again.
So the left subtree has a height of what? Subtree of 10.
There's something productive.
What's left subtree look like?
Zero minus zero equals zero.
For these, it's like 5, right? Okay, so yeah, I'll give it a single node.
It's as full as it can be, and it's got balance heights. It's the same balance.
If it's empty, it has height of negative 1. Okay, so what's the right subtree?
Yeah, two nodes after 5, two nodes after 20, so.
Alright, that's an empty tree, so that's
Negative
negative
1 plus 1 is 0.
Okay, so 0 minus negative 1.
Minus 0 is
Positive 1, okay, so that's balance factor of positive. Alright, so do the same thing for the 20 Yeah, so what's the height of that? So height is the depth of the deepest node, and the depth is the number of steps from the root to that node. So the
server got shit on it. And so now, like, using all
yeah, so the deepest node.
like, I can fix it. But anyways, Alex, they marked me actually. Well, I was like, I don't know.
And then the right subtree is null, which is negative 1, so 1 minus negative 1. Yeah.
Once it sees that.
Alright, so that's the unbalanced tree.
But that's probably
Okay, so once you've balanced for that, go ahead and put in a 40 and see where that leaves you.
Wait, from our new tree or
From your new tree. Yeah, so the old tree goes away.
Are we making from the balance set with previous tree?
Yeah, so after you've got your balance tree, you're going to insert a new node into it.
No, because the right.
It is left. So we got left, which is 1.
No, so this is the balance factor, right? The balance factor is what's on the right. And this tree is 1, I don't know.
No,
The height of this tree is negative.
Yeah.
So the height of this tree is 1. Then you go off of the
0 minus 1.
No, he said from the balance. He said from the balance.
From the balance tree. Yeah, so start with that tree that you had and then put a 40 in. So the whole point of AVL is you always want your tree to be balanced before you add something. I don't know how we best
Negative 1 minus 0, negative 1. 0 minus And that's what the other side is less than one, so.
What if you grasp one of those notes?
0 plus 1 is 1.
Yeah, so it's, yeah, negative 1 is this is like, right,
Left minus right, 0 minus negative 1 is 0.
all right, and then go ahead and put in a 60.
So now it's like this.
We choose 10, 5, 40,
You getting it?
Because when you have nothing on the other side, nothing, well,
So you
negative 1 minus,
Or no, is this negative 2?
but in general, I there's one thing on the other side, so there's one that
40,
negative 1,
20.
negative 1 from,
Yeah.
technically negative 1, this doesn't have to one, it has to
10, 40,
Yeah.
it's a negative 1.
40. It's technically 0 minus 1. It's the same thing. This is the left side tree. Which has a height of 0.
Oh, yes.
And this is the right subtree, which has a height of 1. Yeah, when you're calculating balance, you go 1, 1, 2, it'll get the same answer. So you can do that. Alright, so that's balance. Yeah. So go ahead and add a 60 and then recalculate balance factors.
Question is,
So I think, you just have this one.
in terms of this,
The height of this is negative. Yeah, if you're doing this height is, and the height of this is 0. Yeah, I think, I'd probably do like a different version of height.
Well, I'm not-
Yeah, I just want to catch it right.
it's just 1 minus.
Toss that nose.
Technically,
Technically, this would be 0. The height of this is right for only 1.
Well, the problem is if you're doing it in code that.
These two are the same, like,
Yeah.
integer, that's just this node. No, I understand.
Probably do that if you.
It's just like looking at that, I'm like,
Pass by, anyway, sure, pass by residence.
Makes sense.
oh yeah, that, catch it when you get your hand on it. And even then, I don't get it. Just recursive, I don't get the top of it.
So it's this one that you are interested in, even though they're both negative 2, right? You kind of start from the end and go up, it's the negative 2, negative 1. So it's, yeah, right.
It's like this down to 1.
Yeah.
And then we have to. Yeah, because I think you just have right. Right. And then do just like. That'd be too bad. You probably just have to write it. Yeah, different times. Yeah, no, I mean, it's pretty simple to just take like 1 minus 3.
Oh, yeah. I mean, you can't really have that many issues unless, for whatever reason, you don't leave null.
So I think, so it's like, since we see that we have, like, this is our rate case, so we basically just work with, like, this. So you take it, like, this case and turn it into this. Take that tree, increase the times and.
Because you move the 40 middle and then you move the head.
Yeah, it happens sometimes. But this is the one that's most interesting, because you get the negative 2, negative 1, 0, that's the imbalance point.
Like, there might have been a chance that
I gotta fix that part, and that'll fix the stuff.
Oh, yeah, and then you just call it the other one. Yeah, I think that's a nice one.
So yeah, on this one, it's the 20, 40, 60 that's unbalanced, and And once you rotate that using a right, everything above it will get rebalanced automatically.
We're doing this week, but
Yeah, I didn't manage to get into physics for this corridor last week. Frankly, I'm not, yeah.
it's a fun experience. When I say that with like rigidity.
Like, what's the work is it?
All right, and once you're done with that, go ahead and add a 30.
You wrote 60, you said 30.
Well, we already did 60.
Okay, I forgot that. Do we
I was
get,
behind.
Do we get anything for like notes?
We don't have no like
Check your balance factor.
Oh wait, so are we adding it to the newest balance now?
Yeah, the left tree, the right tree. But it's still balanced.
Generally, from what I'm getting is exactly and then do some like individual. Sometimes it's like a massive difficulty with items. Lack of interest in exams. Basically does, he gives me this example. Way more questions than you're doing. So which I grades based off of, it's like 60% of the places, something like that, is like only available. And if you go over this, grades, it's not you and you do
Yeah, we do it that way.
We go about balancing, but we'll see on Monday.
So 40, 20, 30 is left, right, basically.
probably.
So you got 2 minutes left, so throw in your balance factors and figure out what kind of imbalance this is. What are your balance factors here?
And then what do you do with the right child?
Well, there was that time.
So this was balanced, you didn't need to make a rotation.
this was awful.
I think it's the word unnecessary.
We thought, it's still a binary search tree, right? It's good.
Or you get like, everybody's saying we're gonna balance
But if you on a test, you don't want to do it, right? So
Yeah.
on your AVL, you gotta do this, but, you know, maybe there's a way to make this something better. And maybe that's, you know, right there.
So whichever goes on.
It's still good.
like Google and stuff, they have really good search engines.
Yeah.
Is that just, they just cracked like a really good algorithm for doing reorganizing binary search trees?
So I don't think they came up with like fundamentally new data structure,
Right.
but they came up with new ways to sort of look at information and code it to make it searchable. And in particular, the idea of
So 1900s.
the idea of even search results as the algorithm that decides which search to bring up,
That slows down my learning speed normally.
but they're totally using, the same kind of data structure that we're talking about or that we're using now. A little bit of secret sauce mixed in. All right, so we'll continue this tomorrow. I've made a copy of what the tree looks like at this point. So we'll keep practicing on this tomorrow. If you don't want to hold on to the yellow sheets, I can take it back and I'll bring them in tomorrow. But if you want to play with it, you can hold on to it.